Hello everyone. Today we will start the new topic. The topic name is half wave rectifier. Okay. I already did one video of half wave rectifier, but that one is with the op amp. Okay. But today we will do the half wave rectifier with the diode. Okay, the basic one. First we need to know why we need to use the half wave rectifier or why we need a rectifier. Okay. So first go to the background of the rectifier. If we need to know the background, then we need to know the power supply. Okay. What is a power supply? Power supply mean in any electronic devices or any electrical devices, we need some power to turn on that particular devices. Okay, that is called the power supply. For the power supply, here we are talking about the DC power supply. Okay, DC power supply mean the output will be DC. Second, the output voltage is around 1 volt to 24 volt DC for the power supply. Okay, and another thing will be the frequency will be 0. Okay, these three conditions. So we need to know the basic block diagram of the power supply. Okay, so let's go to the next slide. Here you can see this is the basic block diagram of a power supply. Okay, I already told you for this one we are saying that DC power supply whose voltage range will be 0 to 24 volt. Okay, frequency will be 0, right? But in our normal power supply, that is our home power supply, okay, that unit have the 230 volt or 240 volt AC power supply. Okay, and the frequency is around 50 hertz in India. Okay, like in Taiwan, the voltage is 110 volt and frequency is 60 hertz. This one is used in Taiwan or in America. Okay, but 230 volt to 40 volt 50 hertz power supply, that one normally we used in India. Okay, and also used in Britain or Europe. So you already understand the problem, that is we need a DC power supply of 0 to 24 volt with 0 hertz frequency, but our home power supply is a 220 to 240 volt AC power supply with a frequency of 50 hertz, right? That means we need to convert this 240 volt to 24 volt, right? That means we need to step down the input voltage and go to the desired output voltage, that is 24 volt. Okay, so that means we need a transformer. What is a transformer? Transformer is a device which we can use for a step up or step down the voltage or current, right? For a step up transformer we can increase the voltage, like if we give 24 volt input we can get output around 240. Okay, if we use a step down transformer we can give input around 240 volt and we can get output around 24 volt. Okay, so this is step up, this is step down. Okay, that means for the step up the voltage is increasing. Okay, but at the same time the current will decrease. Okay, so a step up voltage transformer will ultimately decrease the current. Okay, that means the power will be constant. Okay, so a transformer can amplify the voltage or current, but it cannot amplify the power. So V multiplied by I will be kept constant. Okay, and another thing will be the frequency will be constant for a transformer. That means if you give an input of 50 Hz frequency sine wave, then the output will be 50 Hz frequency sine wave. It cannot change the frequency of the input voltage. That means we already here get the output voltage will be 24 volt 50 Hz, right? That means here will be a sine wave of 24 volt 50 Hz. Okay, but here you can see we already achieved the desired output level, right? But you can see here our next criteria will be frequency should be 0 hertz, right? But here you can see our frequency is around 50 hertz. So what we need to do? We need a converter, right? That converter should convert AC to DC. That means we need a device in which if we give a AC voltage, it will give us a DC voltage. Okay, or a pulsating DC voltage. That device called rectifier. Okay, so you already understand. Rectifier is a device which can convert AC signal to the DC signal. Okay, and here you can see in the image, this is a bridge rectifier. Okay, and our today's topic is the rectifier. So in the next slide, I will explain you the types of the rectifier, and today we will discuss about the half wave rectifier. Okay, but one problem is the output of the rectifier is a DC. Okay, is not alternating but is a DC. But the problem will be frequency will be 100 Hz or 50 Hz. Okay, for a half wave rectifier, the frequency will be 50 Hz, but for a full wave rectifier, frequency will be 100 Hz. Okay, so we get a DC voltage, but frequency is not zero. That means we will not get any steady state DC voltage. Okay, so we already converted the input from AC to DC. Okay, but this one we call as a pulsating DC. Remember this one, this name, okay? This is not a pure DC. This is a pulsating DC, right? So if we start from the beginning, we use a transformer to step down the voltage from 240 volt to 24 volt. And after that, we use a rectifier. That one convert the AC voltage to the pulsating DC voltage, right? So now what we need? We need a filter. What is the purpose of the filter? Filter will convert the pulsating DC voltage to a pure DC voltage. Okay. In my last class of the op-amp, previous year question of the op-amp, I think you already have the concept of capacity filter, right? I already explained about the capacity filter with the different time constant, right? So when I will complete the rectifier topic, at that time, I will again explain the filter. Okay. So next is the voltage regulator. Okay. Why we need a voltage regulator? Suppose you have a power supply, okay, with a frequency 0 volt and 24 volt DC, okay. That means you already have a voltage source with a curve like this. That means a pure DC 24 volt voltage source, okay. So now you can see we already have the voltage source, but why you need a voltage regulator? Let's see. Here, I just told you, suppose you have a power supply, okay? This is suppose is a power supply or voltage supply, okay? Here we have a plus, here we have a minus. And you connect a load. This is the RL, right? That means, suppose this is a 24 volt power supply. So, what you expect? You expect that the output voltage across the load resistance should be 24 volt, right? But this is not the case. Why? You all know that this circuit can be converted to a voltage source with a series resistance RTH as per the Thevenin's theorem, right? Now you know that RTH cannot be 0, and here the voltage source voltage is 24 volt, right? So if you calculate the voltage in this point A and B, that voltage will be VAB equal to 24 multiplied by RL plus RTH. Okay, as per the voltage division rule. You already understand that this one, this factor, value of this factor should be less than 1. That means VAB should be less than equal to 24 volt, right? This is the concept of loading effect. That means if you change the resistance value RL, then the output voltage will be changed, right? That means the output will be not constant. That output voltage is completely dependent upon the output resistance, right? But when you buy a power supply, what you expect? You expect that I will connect any resistance to the power supply, the output voltage should be the same, right? That is why we need a voltage regulator. And what voltage regulator used? We use a Zener diode or a conventional voltage regulator like 7805, 7812, like this. Okay, this is the IC number of the voltage regulator. Okay, so that's why we need a voltage regulator. After the voltage regulator is done, then we already make a power supply. Okay, so this whole thing is the DC power supply of 24 volt 0 Hz. Okay, and Transformer, in your syllabus, you don't have the transformer, so you don't need to study that one. In your syllabus, you already have the rectifier, you have the filter, and you have the voltage regulator. Okay. So today our topic is the rectifier, and today we will discuss about the half wave rectifier. In the next class, I will discuss about the filter, and after that one, we will start the voltage regulator with the generator. Okay. So now go to the next stage. So our today's topic is the rectifier, right? What is the purpose of the rectifier? Rectifier purpose is, suppose you have a AC voltage, okay, and you need a DC voltage. That means only one side. So what you need to do? You need a device called rectifier, where you can give a sine wave AC and it will give you the pulsating DC. Okay, this is the sine AC. Okay. Now we have a couple of types of rectifier. Okay. So the rectifier can be divided in the two part. First is the half wave rectifier and another is the full wave rectifier. You already understand from the name what is half wave. Half wave means the rectifier will rectify only the one half cycle of the voltage. Okay. And again like this. Again like this. Okay. So this is a half wave. And what is full wave? This one is a full wave. You understood? Okay. So this is the half wave rectifier, this is the full wave rectifier. But for the full wave rectifier, we have two types of full wave rectifier. One is the center tap full wave rectifier and another is the bridge rectifier. Okay. I will explain you both the rectifier in the next class. Today's topic is half wave rectifier. Okay. So I already told you that we will use diode for this rectifier, right? To build this half wave rectifier. So now you need to know the what is a diode, the basic concept of diode. I will not go so deep inside the diode, but I will just tell you how to use a diode in a rectifier. So first is the, you can see this one is the diode. Okay. And the symbol of the diode is this one. So this is the symbol of the diode. Okay. And you know that for a diode, if I connect, this is the P, this is the N, right? If I connect a voltage source like this, if this is a positive voltage source, then this one we call it a forward bias, right? And if we connect a diode with the voltage source negative with the P terminal and positive with the N terminal, then we call it a reverse bias, right? Or in another word, we can say if this point potential is V1 and this point potential is V2, okay, we can say if V1 greater than V2, then this is the forward bias, and if V1 is less than V2, this is the reverse bias. Okay, so this is for the ideal diode. Okay, so you understand, if we use the ideal diode and when that diode is a forward bias, at that time that diode will be act as a short circuit. Okay, you can see this is short, right? That means if you just increase a little bit voltage, the current will be just rise up like this. This is the characteristics of the ideal diode, right? For the practical diode, how it looks like? It looks like this one. But for the ideal case, it will be straight line like this. Okay, as you can see, this is the short circuit. That means with a small amount of voltage, it will directly rise. Okay, and for the reverse bias, this is the reverse bias condition. For the reverse bias, what will happen? The reverse bias, the diode will not conduct in any case. That means it will be open circuit. That means if you increase the voltage in the negative direction with the minus infinity voltage also, this will be open. Okay. So in summary, ideal diode, forward bias, short circuit, reverse bias, open circuit. Okay. Now go to the practical one. Here you can see this is the characteristics of the practical diode, right? And this one is the 0.7 volt. Okay, so the condition is the same. When V1 minus V2 is greater than 0.7, at that time we will call this one is a forward bias. Okay, and when V1 minus V2 less than 0.7, at that time we can call it a reverse bias. Okay, so this is the condition when we will use a practical diode. Okay, and as you can see, this is 0.7, that means the barrier potential. So that means when we will use a practical diode in the forward bias condition, it will act as a 0.7 volt voltage source. Okay, for the reverse bias, it will be open circuit. Okay, so this one is for the forward bias and this one is for the reverse bias. Okay, so with this concept, I will start the half wave rectifier. Okay, here you can see this is the circuit diagram of a half wave rectifier where we have a input AC voltage Vi, okay, and that input AC voltage should be 24 volt 50 hertz. That means this AC voltage is just after the transformer, that means the output of the transformer, this one. Okay, and here you can see it consists of only a single diode, right? Now I will explain you the circuit operation with the positive half cycle and negative half cycle. Okay, so this is the input voltage, that means V input. Okay, and this one is the time, and this one I am drawing the V output. Okay, so for the first half cycle, when the input voltage is positive, this is the V1 and this point is the V2, right? That means this point is V1 and V1 is positive and V2 we can say is the ground, right? Just to the ground. So we can say V1 is greater than V2, right? Whether V1 is greater than V2, at that time we can say this will be in the forward bias, right? Forward bias, right? As we are using a ideal diode. Okay, so as we use the ideal diode for the positive half cycle, for the whole positive half cycle, this diode will be in the forward bias. Okay, when this is plus, this is minus. Okay, so we can redraw the circuit like this. We already told you this diode is in a forward bias, right? That means we can draw a short circuit instead of the diode, and here will be the input voltage Vi, and here is the resistance R. Okay, RL. So what will be the output voltage across this one? V output. What will be that voltage? The whole Vi input voltage absorbed by this load resistance, as here diode is not consuming anything. Okay, if you want to see, I can do that one. IL will be Vi by RL. Okay, and we can write down V output will be equal to RL into IL. That means will be Vi. Okay, so in the positive half cycle, this will follow exactly the input waveform. Okay, understood? Now go to the negative half cycle. So we already deal with this one, okay, and we already got the output voltage is like this, right? Now we need to deal with the negative half cycle, right? In the last slide, I told you for the positive half cycle, this one is plus, this one is minus, right? So for the negative half cycle, what will happen? Sign will change, right? That means this will negative and this will positive, right? So this is negative and this is positive. Okay, so you can understand here this is V1 and this is V2. As you can see, V1 is negative, right? If V1 is negative, if V2 is 0, then also we can write down V1 is less than V2, right? If V1 is less than V2, what we can write down? We can write down this diode is in reverse bias, right? As this diode is in reverse bias, what will happen? We can redraw the circuit like this. This will be open circuit, right? As this is open circuit, that means there will be no current flow through this particular circuit. That means I equal to 0, right? As IL equal to 0, the output voltage will be RL multiplied by IL. That will be equal to 0. So in the say negative half cycle, we will get a zero voltage. Okay, so output will looks like for the positive half cycle, it will directly follow the input voltage. For the negative half cycle, it will be equal to zero, right? So you understand why it is called half wave rectifier? It is called half wave rectifier as this is just rectify the half wave of the circuit, and another half wave is so zero, right? That means we only got the positive half cycle, no negative half cycle, right? Now I give you a homework. Can you draw a circuit for which the output will be positive half cycle is zero, negative half cycle is looks like this one? Can you draw this circuit? From where we will get this kind of output, okay? If you can draw this circuit, you can directly send me the circuit to the WhatsApp, okay? Now I already told you the ideal condition, right? So what if we use a practical diode? Suppose we think that this is a practical diode, right? At that time, what will happen? You all know that the diode will be forward bias when V1 minus V2 equal to greater than equal to 0.7 volt, right? That means if we give input voltage of 0.1 volt, then this diode will be turned off. 0.2 volt turned off. Up to 0.7 volt, this will be turned off, right? When the voltage is 0.70001 volt, at that time, what will happen? This diode will be in the forward bias, right? That means this diode will be in the reverse bias when input voltage is greater than 0, less than 0.7, right? This will be in the reverse bias for the diode. Okay, when 0.7 greater than Vi, then it will be forward bias, right? And we already saw that if diode is a forward bias, the output voltage will be same as the input voltage, right? So what we can see, this one is the 0.7. Okay, with this time, this voltage is 0.7 volt. Okay, so what kind of waveform we can see? We will see that output waveform will start from this line. Why? In this particular point, diode will be in the forward bias, and in this range, diode will be in the reverse bias. Okay, so we will get the output voltage. But you can see here this is sine wave, right? That means this one is also 0.7, right? That means in this timeline also, this diode is in the reverse bias. Okay, so what we will get? We will get a waveform within this particular range. Okay, and if this is V, then what will be the value of this one? This one will be V minus 0.7. Why? This 0.7 volt will be consumed by this practical diode. Okay, so the output will be looks like start from 0, then like this, then again 0, and then negative 5 is the 0. Okay, so this is for the practical half wave rectifier, or when you use a practical diode, at that time you will see the circuit like this. Okay, in your exam with the concept you need to do the calculation of the VRMS, okay, and V average. Okay, so you need to calculate VRMS and V average, right? As you already understand the concept, the V average and VRMS is just the calculation, right? So that calculation you can easily do that one, and in any book you can get that particular calculation. In the pin comment, I will give you the link of the my handwritten notes where you can get the this V average and VRMS calculation. Okay. If I do this one in the video, that will be much longer. Okay. Now go to simulation and just see how the circuit works in the simulation. So this is the half-wave rectifier circuit. Here you can see this is the AC input voltage source. Okay, here I connect the load resistance and a diode, and here we have a green voltmeter for the output voltage, blue voltmeter for the input voltage. Okay, so let's simulate this circuit and see the waveforms. Here you can see the green one is the output and blue one is the input, right? So if I pause here, you can see that The green one is just for the positive half cycle. We can see that the diode is conducting only in the positive half cycle, right? That's why we get the output voltage across the load resistance only in the positive half cycle, right? And in the negative half cycle, you can see the output voltage is 0, right? So it is just working as a half-wave rectifier. And you can see that this is a practical half-wave rectifier. That's why the input voltage, you can see the max and min is plus 10 volt minus 10 volt, right? But if I click on the green one, the output voltage is 9.21 volt. That means there is some drop across this particular diode around 0.7 to 0.8 volt. Okay. I already show you that this diode will conduct when the input voltage is just greater than 0.7, right? So if I change the input voltage 10 volt to lower one, then you will understand this one. You understand that this diode will work just when the input voltage is greater than 0.7 volt. Okay. Now here you can see the difference very easily. Here you can see that here the E is just around 636 millivolt, right? That means this diode will turn on when it's around 0.6 to 0.7 volt. Before that one, the green waveform is not perfectly follow the blue waveform, right? Not follow the input waveform. Why? As this is a practical diode, and practical diode will not work until the input voltage cross the drain potential voltage, right? Here you can easily saw that one, okay? And when I increase the voltage, at that time you can see at that time, you can see that one negligible, right? A 0.7 volt in front of 10 volt is very negligible. Okay. So this is all about the half wave rectifier. In the next class, we will discuss about the full wave rectifier, center tap, and the bridge rectifier. Okay. Thank you. Bye bye. Thanks for your time. Please do share this concept with your friends. And if you like this video, please press the like button. It is really means a lot for me. Bye bye.